Okay, our next speaker is Sophia Domokos from University of Technology. Take it away.
Thank you so much. So thank you, first of all, actually, to the organizers for putting together this really nice program, and also for giving me the chance to speak. So it's a super, super big honor to be talking at Jeff's 25th birthday party. So what I'm going to be talking about today is holography in the probe approximation and beyond. And I'm pointing the thing at the wrong place already. Maybe, right? There we go. Okay. So the reason I've got a fairly broad topic is because I want to give you a snapshot of some cute results from 2 ongoing collaborations with other Jeff progeny. First part of the talk is going to be about work with Andy Royston, who is very, very sorry he couldn't come today. He wishes Jeff happy birthday, but as you guys can see, he has the cutest excuse imaginable. The second part of the talk is going to be on work with Nelia Mann, who's sitting right there in the audience, so you can direct all questions to either her or to me. Okay, so quick outline for my talk. I'm going to start out with some background that you guys all already know. But what I learned from Jeff as a student, the way he was with me, was that he would tell me a lot of things in a very simple, beautiful way that I understood completely. And then he would ask me a question to which I had no idea what the answer was. And then I would have to go back to my office and think for like 4 weeks. I don't know if I can provide the latter, but the former, hopefully I can do. Then the first part of the talk, I'll talk about really what we mean by the probe approximation. So this is kind of a slight elaboration on the things that you guys have all already heard of. And I'll talk about a few cute results from supersymmetric brain intersections. And then I'll talk about going beyond the probe limit in holographic QCD models, and just a snapshot of some nice results with Nelia Mann. And then at the end, I will say a few words about El Jefe, as we used to call him in graduate school. Okay, so things that you all already know. So what do we mean when we say holography? For the purposes of this talk, I'm just talking about generalized versions of ADS-CFT, mapping strongly coupled gauge theories, or also gauge theories with some defects and stuff, to weakly coupled theories of supergravity. The whole point of the idea being that you can use the weakly coupled supergravity to understand something about the strongly coupled theory. This is obviously a huge program. It's been used to model in real world applications strongly coupled QCD. I'm mentioning this because this is an area where Jeff has done some nice work. Very nice work, I'm saying, because I was a co-author on many of those papers, as were Andy and Nelia, a few other people in the audience. It's been applied, of course, to condensed matter systems and then myriad applications, some of which we've heard about today. Okay, so just to kind of remind everybody about what we mean by the holographic limit. So we start out with a stack of NC DP branes, just taking P to be general at the moment. And then we take a low energy or near horizon limit, by which we mean that we take the string length to be small. I don't like things with dimensions to be small, so I'm just multiplying it by some scale mu, which we can think of as some renormalization scale here in the field theory. Okay, so while we take the string length to be small, we also hold fixed dimensionless Yang-Mills coupling on the DP branes, and also the energies of some characteristic processes. So kind of doing all of this stuff, we end up with these 2 separate sectors which are supposed to be dual to each other. On the one hand, we've got P plus 1 dimensional super Yang-Mills. And on the other hand, what we've got actually is closed strings living in the near horizon geometry of these DP branes. But if I go a little further and take this theory to be at large NC and large Hooft coupling, then what I end up with is supergravity on ADS. Okay, this is actually slightly more subtle than what I'm saying here when P is not equal to 3, but for our purposes right now, this is fine. So this is all nice, but if you want to study, some kind of fundamental matter, you want to add in some other degrees of freedom, and you can do this by adding in a stack of NF DQ branes. So what does this look like from the perspective of the duality? Basically, it means plonking a defect onto both sides. A more technical version of saying Planck is the probe approximation. Okay, so what do we mean by a probe approximation? On the gravity side of the duality, this means suppressing all back reaction by those extra D-Branes. And also, as a consequence of this, it also means suppressing interactions between closed strings and the open strings. From the field theory side, if there are any people here kind of imbued in the lattice literature, this is the quenched approximation. And it also means technically that there are no meson glue ball interactions. So we sort of focus on either the glue ball sector, meson sector, and that's it. Okay, so now let me tell you about this slightly stricter version of the probe approximation that kind of came out as a consequence of some things that Andy and I have been thinking about. So the motivation actually came from holographic QCD originally, although we now sort of have broader ideas. And the sort of story with holographic QCD is that it's been surprisingly successful for describing mesons and gluons, because those are open and closed string states, relatively easy to deal with in supergravity. But baryons, even to this day, are still a challenge. I think Jeff actually gave me my first project was something to do with baryons in holographic QCD. It was super hard and I failed at it completely. It is still a challenge today. There's been, a lot of beautiful work in this area, but why is it so hard? Well, these baryons are dual to solitons on those D-Branes, which especially when you're looking at more realistic holographic QCD type of models, they've got a pretty complicated action. I mean, DBI, Chern-Simons, all of that stuff, they're living in a non-trivial gravitational background, etc. Okay, so there's been a lot of nice work, but it relies on a lot of, pretty big approximations and or numerics, okay, which is, all very nice, but there are a lot of questions that it's very, very hard to answer. So anything about dynamics, let's say, would be pretty difficult to answer. So one kind of thought that Andy and I had was that, maybe we can learn something by looking at a different kind of simplification. Which is to say, okay, let's look at something which is clearly not QCD. Let's look at some supersymmetric Yang-Mills-Higgs, but on curved space. That is, the thing that lives on a D-Brane intersection, just with a kind of more strict version of the probe limit that we know and love. So the original idea for what we were hoping to get out of this was sort of an easy toy model for studying solitonic objects. Here I'm leaving P and Q fairly general. So these are sort of generic solitonic objects on defects. This is, of course, unrealistic to QCD and to any other real-world system, but having supersymmetry would put a lot of tools at our disposal. It would be easier to find these solitons in the first place. So, the pie-in-the-sky idea from the start was maybe to find hints at underlying structures that are there in hadron physics. We are definitely not there yet. I'm not going to promise anything on that front. But as we've discovered, there's a lot of interesting stuff to find here, even just, in the supersymmetric case. So the shorter term goal is kind of a deeper understanding of ADS CFT with some defects. Okay, so let me just tell you our key results so far, most of which I will not describe in detail. So we derived this sort of stricter version of the probe limit with non-abelian defects, where the theory on the defects is an SUNF super Yang-Mills on rigid curved space. And the reason I want to emphasize this is many times in this talk, I'm going to say super Yang-Mills. Almost always I mean super Yang-Mills in curved space on the supergravity side of the duality. Another cute result that I will talk about is a really intricate and interesting zero energy vacuum structure, where within the zero energy vacua, we actually include moduli spaces for particular separate cases of monopoles, instantons, and vortices. Some results that I won't talk about have to do with the D3, D5 system, where we derived a fully gravitationally covariant curved space super Yang-Mills, including all of the fermion stuff. This was a pretty non-trivial task, but isn't that interesting to go through with an audience. And from that, we also derived BPS equations for a zoo of soliton states. So those I will not talk about much further. Okay, so what precisely are the systems that we're talking about? So here we're limiting ourselves to supersymmetric DP-DQ intersections. Let me just talk quickly about what all the different kinds of coordinates are, so we're all on the same page. So we've got NCDP branes. These are the ones that we're looking, who are providing the gravitational background. So the directions along which both these guys and the flavor branes are extended, I'll label with X mu as usual. The color branes are extended also in these additional directions that I'll label with Y. Then, of course, we've got directions where neither set is extended, so we can actually provide a gap in the theory by separating these guys out along this Z direction. And then we've got these directions where the Q branes are extended, but the DP branes are not. So these are directions that do not appear in the dual field theory, but they are going to play a kind of interesting role. So the curved space super Yang mills that I've been talking about lives on the X, mu, and R directions, so on the world volume directions of the DQs. Okay, so how do we find the probe approximation? Well, the action here is, of course, the supergravity action plus the action on the DQ branes, which is just dBi plus Chern-Simons. I wrote out the dBi part of it, just to remind you that it, of course, includes interactions between brane modes and bulk modes. Okay, so it's all kind of in there. All of this, back reaction stuff that ought to be happening is contained inside of this action. Okay, so what do we mean by this particular version of the probe approximation? The sort of standard one that until this point in my life I thought of as just NF much, much less than NC, is suppressing brane bulk interactions. The stricter version is to just cut off all of this dBi stuff at super Yang mills. Okay, so how do we do this? Well, in a fairly trivial way. So first you do some kind of nice rescalings of the various fields involved. And then you just kind of expand order by ordering fields. So this looks more complicated than it needs to be. These are just some factors that come from the metric. R is basically the radial ADS type coordinate. And then we've got these vertices. Each vertex contains NO brane type fields, which include all of the ingredients you want in super Yang mills. So, non-abelian field strength, covariant derivatives, etc. And NC supergravity field, so these are graviton, dilaton, etc. So the expansion is, of course, controlled by essentially alpha prime and kappa. So these are epsilon and kappa. These are sort of rescaled versions of all of these things. There's also an additional Yang-Mills coupling. So this is not the Yang-Mills coupling we held fixed. This is the Yang-Mills coupling of this particular super Yang mill. So if we want to make our lives easy and just kind of isolate to tree level, we're also going to treat this guy as a small parameter. Okay, so this looks totally straightforward. You say, okay, I just want the V20 guys. That's the Yang-Mills. So I'm just going to say that all these three parameters are small. Which is exactly what you want to do, except that there are actually terms which are lower order in these small parameters. So what are these terms? So not all of them can hurt us, but let's talk about what they are anyway. So the first, or the 0th term, is simply proportional to the energy density of the brane, which just gives you, NF times the tension. There is no V10 term, so that would be linear in the brane fields. This is for supersymmetric embeddings or just any situation where the probe branes you put in minimize their energy in the background. The guy that in every paper that I had seen so far was completely ignored is this guy, which is a closed string tadpole. It appears from expanding the dBi action. And this one, in principle, it could cause you some problems because it's at lower order in all of those small parameters. But if really all you're interested in, is the interactions between the open string fields, then the only way, this guy can cause trouble is via corrections to open string processes. Okay, so that means that we can actually ignore it if we realize that it's always going to come coupled with another vertex. Okay, and it's this combination of these two vertices that I need to be small, which crunching some numbers gives you a slightly more complicated bound on NF over NC. Okay, I'm going to say a few more words on this in a moment, but I just want to point out there is actually one more kind of lower order term here, which is going to be the star of the show in the second part of the talk. For now, as long as I'm only looking at the SUNF sector here, I can just kind of ignore this guy. Okay, so this is the probe approximation. We've got some limitations here. This is from keeping those 3 small parameters small. These are just kind of various versions of keeping the 't Hooft coupling small and NC large, or sorry, 't Hooft coupling large and NC large. And this is the actual probe limit that tells you how to neglect the back reaction. And the reason I want to pause on this is because in the case where Q is equal to P, so where the dimensions of the color and flavor branes are the same, this reduces to NF over NC much, much less than 1. Okay, but when Q and P are different, then we get these extra factors of the 't Hooft coupling. And if you think about it, it does make sense that you should have something like this, right? Because when you're comparing, let's say, D3 branes to D5 branes, in some sense, you're comparing apples to oranges, right? The D5 branes have 2 dimensions along which they might be infinitely extended where the D3 branes are not. So that consideration is somehow bundled into this 't Hooft coupling factor. Okay, so that's the story. We end up with some super Yang mills here. I've just written the part with the bosons. This is, super Yang mills. I've got a Chern-Simons term as well. And now what can we get out of this? So I'm just going to tell you a tiny bit about the space of vacua here. Okay, so we're looking at things which are absolute minima of the energy, okay, for which we're going to examine the Hamiltonian, okay? And the Hamiltonian we'll see consists of kind of the normal kinetic piece, but a slightly unusual potential that's going to yield something. But before we do that, let me just, instant remind you of the Hooft-Polyakov monopole, which will help me explain why that thing is cool. So the Hooft-Polyakov monopole here, I've just got, Yang mills, Higgs. I'm looking for monopoles which are localized in space, time-independent finite energy states. And the nice way that you can, first of all, derive an equation for them and understand the relationship between the mass and the magnetic charge is by doing this Bogomolny trick in the Hamiltonian, right? So neglecting all, time-dependent pieces, I've got a Hamiltonian, which is magnetic field squared plus gradient of phi squared, okay? And then the Bogomolny trick is to add a boundary term, which lets you complete the square. Okay, and this tells you that if I make this term 0, okay, then that will give me a lower bound on the mass, which turns out to be proportional to the magnetic charge, and it gives me an equation for these states. Okay, but I had to add and subtract, or Bogomolny had to add and subtract this boundary term. Now, what happens in this situation, the brane intersections is a little bit different. So let's look for now just at a D3, D5 intersection. So this is one which has long been studied in holographic contexts, where we've got 3 directions along the D5 branes, which are extended while the D3 branes are not. Okay, so we've got kind of usual pieces that come from the DBI action into my action. But then we've got this kind of slightly unusual thing that comes from the Chern-Simons term. Another interesting thing I learned from Jeff is that the Chern-Simons term always contains the most interesting stuff. And then that's the case here too. Because what does this term do? It actually completes the square automatically. I didn't have to add or subtract anything, right? So, I have supersymmetry here, so maybe I should have already expected that something like this would happen. But the way that it happens is kind of nice because you end up with this exactly, Bogomolny-like equation on these extra directions. So these are the directions where the D5 brane is extended. Okay, the D3 branes are not. So these are not describing, monopole-like states in the dual field theory, right? These things are extended in the dual field theory. What they probably, I guess I would term them in the dual field theory is describing some kind of super selection sectors, right? So these are not particle-like states there. Because in fact, here they have 0 energy. They also preserve the same number of supersymmetries as before. And you might be thinking, well, I've kind of heard a similar story. And we think, although we have not made this precise in any way, that there should be a connection to this old story by Diaconescu and Hanani and Witten, where these D3 brane segments are realized monopoles in the world volume of these D5 branes. Okay, and what's happening here is that we've got these extra D3 brane segments, these monopole-like vacua, I want to say, are these D3 segments, but we've also got this D3 stack. So in some very, very vague sense, we've taken, some number of we've got a lot of monopoles here. We've taken some number of the monopoles or 't Hooft defects to infinity, might be the idea. We have not made this more precise. Maybe people here have some more better ideas about how to do that, but we think some connection like this should exist.
They don't affect the physics on the flavor branes?
They do. I mean, they have a magnetic charge.
Could you flip the earlier slide? I'm just trying to get in my head what's going on.
Yeah. So the R directions are, again, directions where D5 is extended, but D3 isn't.
So, all right, so these vacua are just classified by an integer, which is the magnetic charge associated with this ammonia equation.
Yeah, exactly. Okay, so a few more notes on this. You say, okay, we did this in D3, D5. That's always the easiest case. D3 branes, starting with D3 branes. You can do this for DP, DP plus 2 intersections. The story plays out in more or less the same way. And something that is kind of nice here, you end up with, exactly the same Bogomolny type equations, but actually the metric according to which you've got this Bogomolny equation is a little bit different. So these states are now living on a metric which is conformal to a cone. Depending on the dimension of P, this is a cone with an excess angle or a deficit angle, which I have no idea what to make of this. I mean, I think this is something that would be nice to understand what the field theory interpretation is. When P is equal to 3, this just reduces to flat space. So that's kind of an interesting story, and I won't go into the details of this, but you can play out the same idea for general, quote unquote, soliton-like vacua. Where again, you're just playing with how many extra directions you have in the curved space Dubry angle. So these directions where the Q branes are extended, but the P's are not. The form, of course, of the solution depends on the dimension of the transverse space, but again, from the Chern-Simons term, you always get this completion of the square. In 4D, you get Euclidean instanton-like solutions. 3D, as I've shown, you have monopoles. And 2D, you have something that looks sort of like vortices. Okay, so you have this kind of realization in all of these systems.
What's the space that has the deficit angle?
So this is the space that the monopoles live on. So this is not slightly technically, what happens is that in the Hamiltonian, you get some kind of extra metric factors on here. Which turn out that if you do a rescaling.
Normally I think of a conical deficit as indicating there's some kind of a line source, like a cosmic string. So is the monopole?
Is the monopole that line source?
Yeah.
I'm not sure, and so the reason I'm saying I'm not sure is because this is the case where I haven't moved the brane stacks apart at all. So in that limit, often I actually can't I'm not sure that I can trust the geometry the supergravity at that point anyway. In those situations, if you move the brane stacks apart, you get a slightly more complicated version of this metric, which kind of smooths out the bottom of the cone. Okay, so let me just quickly summarize part 1. I think I'm doing okay on time. So what I told you about was sort of how to make the probe approximation that we all use all the time a little bit more precise. I told you about the vacuum structure, which involves these weird soliton-like vacua. As I said, we also found a whole bunch of BPS equations. The future is really to sort of try to understand all of this stuff more precisely from the field theory side. So first of all, in the dual field theory, it would be interesting to sort of understand how that combination of 't Hooft coupling and so forth comes out. And of course, then to just look at the holographic duals of the soliton vacua and the soliton. So this is kind of where we are headed at the moment. Let me now do kind of a switch of gears to talk about what happens now if we go beyond this probe approximation, and I'm going to talk specifically in the context of the WSS Witten-Sakai-Sugimoto model of holographic QCD. And this is work with Nelia sitting right there. Okay, so first of all, why in God's name do we want to do this? Well, the cheeky answer is to say that NF is of the order of NC in real life, so you should want to understand what happens in your holographic models. There are, also sort of phenomenological reasons to do this. All of these light isospin mesons that we have, in particular the zero spin guys, these are expected to be partly glue ball, so there should be mixing between the glue balls with these states if they have the same spin parity charge conjugation. And also, glue balls decay to mesons, so you will observe mesons. That's one way of seeing glue balls. There's already been some nice work on this by Hashimoto and authors and a number of follow-up papers. Another reason to do this is that maybe this can kind of clarify some pretty big issues in top-down holography. I'm saying clarify to not be too ambitious. So what are these problems? Well, all of these top-down holographic models, by top-down I mean, built within some critical string theory, they suffer from the problem that, they suffer from a number of problems, but one of the problems is that they have a lot of spurious states, right? So because you have these extra dimensions, you have a bunch of states that don't really seem to appear in the spectrum. And so one question is that, okay, well, maybe if you go beyond, NF much less than NC, maybe something will happen to the spectrum and you'll get some states lifted, maybe something miraculous can happen. If not, it'll mean that there are additional problems and these models are just good heuristics, but not more than that. Okay, so let me quickly just review the Witten-Sakai-Sugimoto model. This is one that's probably familiar to many people. I know many in the audience have done work on it. So the idea here is to take a stack of NC-D4 branes. These guys are going to provide the background, and to compactify them on a circle. Okay, so this was Witten's idea. And the nice thing that this does is provide a confining geometry. The idea of Sakai and Sugimoto was, okay, how do we add mesons to this? It's by adding a stack of D8 branes and a stack of D8 bar branes. And the nice thing about this model is that, as with most holographic models, the radial coordinate here is roughly dual to the energy in some sense. So at high energies, these D8 and D8 bar stacks realize the chiral symmetry, but at lower radii and therefore at lower energies, they join together in order to minimize their energy. And here we have the breaking of chiral symmetry. Okay, so the players in this game are the glue ball states, which come from supergravity, and also the meson states, which are basically gauge fields, and just one scalar, which are the mesons living on the branes. In terms of the coordinates, just sort of usual story, we've got x mu. These are the coordinates of our regular field theory. So this is our QCD coordinates. We've also got this tau coordinate, which is the compact direction of the D4 branes. The scale of this tau direction is given by some scale we're going to call MKK. We've got a radial direction along which the D8 and D8 bars are extended, and then we've got this force sphere, which I'm going to just ignore for the rest of the talk. Okay, so this is the setup. And usually the setup is studied in the strict probe limit. Okay, but as we've seen from the first part of the talk, there is some back reaction. Okay, so this is just the part of the DBI action that's relevant to me right now. And just from the pullback of the metric onto the branes, we've got a mixing between the graviton and the scalar, as well as these tadpole type of terms. Okay, so these are the V01 terms from before. These will come out as source terms in Einstein's equations, more or less. And then these V11 terms are going to mix a certain part of the graviton with this one brane scalar that we have in Sakai-Sugimoto. So from DBI, it looks like we have a mixing between glue balls and mesons. Okay, so the main characters here are going to be a few of the graviton components. So these are H tau mu and H tau u. These guys transform like a gauge field in 5D, so in X, mu, and U, defining a 5D space. And these guys are dual to a spin 1 glue balls. And in the background, so without taking into account the inclusion of these extra branes, they have a gauge symmetry that's just inherited from the diffeomorphisms. It's basically showing translations in the tau direction. The other character is this one scalar we have in Sakai-Sugimoto. This is has dual to, it is fluctuations of the flavor branes. This guy's dual to a spin 0 meson. Okay, so the short-term goal is to sort of understand corrections to the spectrum for these states, understand, how this mixing process actually works. The long-term goal is, of course, a more comprehensive understanding of NF over NC corrections. Okay, so something that took us some time to realize was that both of these terms actually correct this quadratic order glue ball meson action with mixed terms at the same order in zeta. Zeta is this parameter. This is actually the same parameter that I discussed at the beginning of the talk, so this is the thing you would need to be small. So you have to treat both of these things at the same time to tell a self-consistent story. So what we did at first was we thought, oh great, well everybody ignores the tadpole, we're just going to ignore the tadpole, and we're just going to look at this V11 term, participating in the quadratic order Lagrangian, and everything is going to be great. And then it turned out that the Lagrangian was kind of garbage, so it seemed like there should be a gauge symmetry. The gauge symmetry wasn't realized. We didn't really know what was going on, and we realized that the solution was that you actually need to include leading order back reaction, because the leading order back reaction comes in at the same order in zeta. Okay, so luckily we were not the ones who had to work out the leading order back reaction in the Sakai-Sugimoto model. This was something that was done by Burrington, Kaplinovsky, and Sonnenschein. They did a really nice job. So they studied leading order back reaction with the flavor branes actually localized. This was a very, very complicated story. The reason it is so complicated for us is that the graviton components that we are interested in don't decouple from the other bulk fields. Okay, so for, as a start, to make our lives easy, we want to just look at the sector where we've got, this one vector and one scalar, and that's it, right? If I take into account, the full back reaction, these guys don't, or the tau-dependent back reaction, they don't decouple. We also, if you include a full back reaction in this tau direction, you can't neglect mixing between different KK modes along this tau direction, right? So whenever we're looking at the spectrum in this model, where we kind of implicitly have a KK reduction, not only along this U direction, that's not a real KK reduction, but we look at sort of a tower of states in U, but we also have a KK tower along the tau direction. And we can't neglect that in this limit. So we decided to start out with something simpler. This is just kind of a smeared out version of this Burrington background. It was written down by Bigazzi and Cotrone. And the idea here, this is fairly standard when people study back reaction in brane intersection systems, is to smear the branes in the tau direction. Now, I don't really like this idea because especially since we have D8 and D8 bar branes, I'm not really sure what it means to smear them all out around the tau direction. So the way that I think Nelia and I both prefer to think about this is that the background given by Burrington and authors was basically a Fourier reduction, so expanding out the background in terms of Fourier modes in this direction. So the way that I prefer to think about it, or we both prefer to think about it, is that we're just taking into account the 0th order Fourier mode there. Okay, if we do that, this does a lot of nice things for us. So The smearing, of course, restores the isometry in the tau direction. This is why people do it. It's easier to find the solutions. And what it does for us in particular is that it restores the gauge symmetry that we had for this mode H in a way which now involves the brane scalar. Okay, so we have this symmetry in our quadratic order action now. And just to sort of very quickly tell you how this goes from here, well, we want to gauge fix. So we end up with just one 4D vector, which we call kappa mu, one 4D scalar that we happen to call omega. And then the action looks something like this. So basically, we've got a quadratic order terms for both of these states. And then we've got this mixing term. Okay, and then all of these A, B, and C's, these are just some metric factors, which using the backgrounds that were worked out by Bigazzi and Cotrone, we can expand out to leading order in this parameter zeta. Okay, so let me tell you about the numerical results. The numerical results were not really the point of this program, so part of the point was just to sort of understand how this decoupling works. But let's see what they are. So we solved the equations of motion for these guys, expanding, mode by mode along the radial ADS direction. This gives rise to towers of blue balls and mesons. So these are not, states along the Regge trajectory. These are on daughter trajectories. And what we end up with is, of course, a one spin, so a spin one state. So this is a 1 plus minus blue ball. And a 0 minus minus meson. So these are now all, of course, partly mixed. But because we're working at leading order in zeta, clearly this is mostly blue ball, this is mostly meson. And we can look at the corrections to the masses at leading order in zeta. So the scale of the mass is set by that KK scale. And then we've got sort of a leading order eigenvalue and then the first order in zeta. I'm not plugging in for zeta because, first of all, for the numerics to work, but actually also for the background solutions to be valid, you need to take this zeta to be very, very small. In real life, zeta is more like on the order of 0.3. So I think it would be deceptive to actually plug in either value of zeta here. But let's just see what direction the corrections move us. So
how do you get the real life value of zeta? Because it involves NC and no.
Yeah, so that's a good question. So in the Sakai-Sugimoto model, you can make predictions for some particular quantities. Usually people use the rho mass and F pi to fix whatever free parameters you have. So that's where we get that value.
Thanks.
Yeah. Okay, so what do we see here? So for these glue ball states, it turns out that they actually only receive corrections from the background. So by doing a field redefinition in the action I showed you before, you can sort of get rid of the the mixing piece from this action. So you can kind of isolate out the contribution. So this guy only gets a contribution really from the parts that come from the modifying the metric. And all of these corrections seem to push the eigenvalues downward. Similar story happens for the meson. So here we can split up the contributions into kind of the back reaction piece and the mixing piece. The back reaction piece again pushes the eigenvalue downward, while the mixing piece actually seems to lift it up, and in some cases, or for the lighter states, it overtakes the back reaction bit. So what this seems to do is kind of for the lower states, like push the eigenvalues apart a little bit. Is this good news or bad news in terms of Sakai-Sugimoto? The answer is that not really sure, it's somewhat mixed. So these 0 minus minus states are not seen in the spectrum as far as I'm aware. So you would want to try to get them out as much as you can. On the other hand, there is also actually a lot of controversy, or we believe there's a controversy around these 1 plus minus states. So there are actually sort of two sets of 1 plus minus glue balls in the kind of original glue ball paper. I think it's not clear which ones are the spurious ones and which ones are the real ones. Yes, question?
Are the direction of the correction the same as the ones from QCD?
Say that again, sorry?
Is the direction, sign of the correction correct from in real life and in the prediction? Especially the delta lambda one.
From QCD, I'm not sure, I don't know.
Like the
how to
mixing
calculate
between glue and meson.
I'm not sure I know. Yeah, I don't think we can
Computed
tell.
What about comparison to lattice QCD? Does these corrections improve or make worse?
So, okay, so the real answer is we haven't done enough states or enough calculation of all of the masses to tell. Because really the only thing that we can know here is ratios of masses. So in order to answer your question, I would need to kind of figure out what the corrections are for all of the glue balls, and then also find lattice results which go beyond the quenched approximation. I think those do exist now, like more than when Brouwer, Matur, and Tan wrote their original paper. But I'm not sure exactly how much data they have. So yeah, so that's kind of an outstanding question.
Are there also 0++ glue balls?
There are there, but they're not involved in the mixing here.
Okay, you have no meson states to.
Yeah.
Pure glue without mixing again?
Sorry?
They're just pure glue. without-
They're pure glue,
without
yeah.
mixing.
Okay, so what I've told you about is this piece of glue ball meson mixing that comes from DBI as kind of a test case as a first step in studying NF over NC corrections. We looked at this kind of isolated sector of the theory. In future work, of course, we'd like to sort of do a more comprehensive understanding, really see how this, shifts the various couplings. Of course, the meson masses are also going to be affected by this. If I change the background, the meson masses will also change. So there should be corrections there as well. Okay, so now I'm going to get to the part of the talk that you all have been waiting for, which is to
All
say.
but one.
So I should say that with Jeff's permission, I have restored some of the more embarrassing stories in this talk. And it's a testament to the fact that Jeff is a very good sport, if not very gracious. And he allowed me to do that. So, as when we were grad students and postdocs, I think we all admire Jeff very, very much. And I think one of the things that we all know about him is that Jeff asks really amazing questions. One of the things you might not know about him is that he asks these amazing questions and then uses them as an excuse to then very quickly exit seminars where he's gotten bored. This was something that used to happen in grad school. So, you're sitting there in a seminar, Jeff asks this question, which is, just kind of like mind-blowingly simple, but really gets to the heart of the matter. And sometimes the seminar speaker is stopped in their tracks and then, they continue on. And as a grad student, you're like, oh, wow, okay, that was a great question. Then you turn around to see again what Jeff is thinking, and Jeff has disappeared. So that was why we started calling Jeff the Pink Panther. Another, testament to Jeff's quality in this regard is that I think only I remember this, but I believe that it is true. So once I was in Jeff's office, I was telling him about some calculation that I was stuck on. I was standing up here at the blackboard and writing, and I turn around, and Jeff has fallen asleep on the couch. He wasn't fully stretched out. It was kind of dozing off a little.
My eyes were closed and I was thinking.
Yeah, he was meditating on the answer. So I cleared my throat a little bit, and Jeff kind of wakes up, and then of course he looks at the thing that I've been writing for probably 20 minutes or something, and he's like, oh, what about that? And of course, then I had to go back and think about that in my office for ages. What I learned from this as a student is that if as a physicist you know how to ask these beautiful, simple questions, other than that you can just do whatever the hell you want. But aside from asking these beautiful questions, I think another quality of Jeff's that we can all appreciate is that he really kind of goes into different areas of the field, and he's willing to come with kind of a humility and just start from the beginning and learn something new. And he demonstrates this in a few other parts of his life as well. So when I was a grad student, it was just around, I think, Jeff's 55th birthday. or 15th, if we said you were 25 today. And a bunch of the other grad students and I were running the Chicago half. And Jeff, who I believe was not really a runner at the time, decided that he was gonna do it also. And he did it. Like it's not trivial to train for a half marathon. He went, he ran the thing. Don't know if he ever ran again after that, but he ran the race, right?
It took me 6 years to recover.
What was his time?
We're not gonna comment.
Let's just say Sophia had completely recovered by the time that I did.
But again, I think this really says something about Jeff's character, and I think it's something that we all appreciate.
It takes over 4 hours to walk that far.
Jeff was running, man. It was a half marathon though, not a full marathon.
I know.
So the final thing I want to say is, I always appreciated Jeff as an advisor, but now that I'm starting to have some advisees of my own, I'm starting to appreciate even more the way that he was really a very careful and supportive advisor. So he knew how to challenge you. He knew how to ask you difficult questions, make you think about things, push you when you needed to be pushed. But he was also endlessly supportive. And as a person who's not naturally super confident, kind of having Jeff there and having Jeff's support, even after I graduated, there were many times I would email Jeff for some Jeff wisdom. It's made so much difference to me throughout my career. So thank you so much, Jeff.
Sophia, questions?
I'm feeling kind of emotional. Thank you. That was really sweet. But if I
He's
try to-
asking his sad question.
Yeah.
if I try to ask so I'm still a little mystified about the physics of these monopoles. Do they show up in the Witten-Sakai-Sugimoto model?
I am not sure. I haven't checked. So there, yeah, I don't know no, okay. So there we have 5 compact, 5 extra dimensions. So they would probably take on a different form. Maybe there is something there. My kind of off the cuff guess would be that the supersymmetry is the thing that's helping them be zero mass. But I'm not sure.
And you're broken supersymmetry.
Yeah, in Sakai-Sugimoto, you're breaking the supersymmetry.
But in these
So-
supersymmetric configurations, you have some super selection based on magnetic or other charges from these
Yeah.
solitons.
Exactly, but again, so if the dual field theory, doesn't know about those extra directions, so yeah, it is just
There's no
some.
subtle way in which they affect the dynamics or show up in some parameters or something?
Well, they probably will show up in some parameters, right? Because all of those extra dimensions are providing some R symmetry, right? So if you do look at sort of motion along the extra directions, that will affect the dynamics somehow. We don't know yet how. That's not something that we've checked.
Okay.
But yeah, that's a question for in the future. Yeah. Yeah.
So just to understand your motivation, so if I'm not mistaken, there are some examples of Brane intersections where the fully back-reacted dual geometry is known, like I think D3, D5 might be an example. But that's not good enough for you because you want to do like non-supersymmetric QCD.
Yeah, I mean, if you want to kind of understand QCD, I mean, I think it is a sort of interesting question to sort of see how this Brane decoupling works. Another reason why those types of theories look a little bit different is because if you're looking at a sort of fully back-reacted system, so many of those are in what's called the Veneziano limit. So when you take both NF and NC to be large and you keep fixed their ratio, that's a different limit than this limit, right? So I don't know exactly what Yang-Mills coupling you keep fixed when you take NF and NC to be large, but it's not the same Yang-Mills coupling that you hold fixed here. Our Veneziano limit theory is interesting for QCD. Yes, there's been, a lot of work on Veneziano limit QCD on kind of both sides of the duality. But the models for that are kind of bottom-up models, as far as I know.
I had a quick question. This sign of the corrections that you're showing.
Yeah.
Is there an explanation for that?
I'm not sure the answer to that, why they come out negative. I
And
don't,
positive. There are two signs which are perfectly.
yeah, these guys. I don't have a very good answer. Nelia, do you have a good answer?
I'm not sure I do.
Yeah, we obviously, we noticed this, yeah, we don't know what the answer is, so that's a good question. I mean, the even better question is that once you study this for a whole bunch of other states, are all of the corrections due to the background negative? Or, is there some situations where it's positive? I mean, we're looking at, one state that's a glue ball and one that's a meson, so that doesn't seem to affect it, but yeah, that's a good question, we don't know.
The questions? Okay, if not, let's thank Sophia again. While you're setting up, our next speaker.